Hello, welcome. In this short video, let us look at the derivation of the PDF of variance estimate from a set of two observations that are independently drawn from a Gaussian distribution with mean 0 and variance sigma square. That is, given two observations x of 0, comma x of 1 taken from a Gaussian distribution with a normal distribution with mean 0 and variance sigma square. So given this information and given the estimate, that is sigma square hat is equal to 1 by 2 x square of 0 plus x square of 1, that is basically average of the squares of the observations. This is a value for the estimate of sigma square. We want to derive the PDF of this estimate. So label y naught as x square of 0 divided by 2 and y1 as x square of 1 by 2. That is, the y naught is 1 by 2 times the square of the first observation, and y1 is 1 by 2 times square of the second observation. Then sigma square hat, that is sigma hat square, is equal to y naught plus y1. Note that since x0 and x1 are independent of each other, so are y naught and y1. Hence, the estimate sigma square hat is a sum of two independent random variables. And for a sum of two independent random variables, the PDF of the sum should be equal to convolution of the individual PDFs. So our first task is to derive the PDFs of these individual random variables y0 and y1. And since x0 and x1 has the same PDF, y0 and y1 should also have same PDF. So let us derive the PDF and the CDF of y0 first. That is, f of y0 less than y0 is equal to, that is the cumulative distribution function, is equal to the probability that x square of 0 by 2 is less than or equal to y0. This is the definition of CDF, and this is equal to, by rearranging, x of 0 is less than square root of 2 times y0, and therefore the PDF of y0 at y0 is equal to the derivative of this probability, which is equal to fx of square root of 2 times y0 multiplied by the derivative of this function with respect to y0, which is 1 by square root of 2 into y0. Therefore the PDF of y0, that is x0 square by 2, is given by, that is y0 of y0 is equal to 1 by square root of 2 times y0 into fx of square root of 2 y0. So this is the PDF of y0, and so is the PDF of y1. Then the PDF of sigma square hat, that is sigma square hat of sigma square hat, that is the PDF, should be equal to the convolution of y0 of y1 fy, the PDF of y0 convolve with PDF of y1. And this is the result from probability theory, that the PDF of a sum of two independent random variables is equal to convolution of the individual PDFs. So by using this formula, we can derive this PDF, and by using the result, the integral becomes, the convolution integral becomes 1 by square root of 2 times tau into exponential of minus square root of 2 tau whole square divided by 2 sigma square. And this is the PDF of x, and at x equal to square root of 2y0, we get this PDF, multiplied by, of course, we have 1 by square root of 2 pi sigma square, and multiplied by 1 by square root of 2 times sigma square hat minus tau, that is the contribution from the second PDF, that is 1 by square root of 2 into sigma square hat minus tau into 1 by square root of 2 pi sigma square into exponential of minus the exponential part of normal PDF, which is square root of minus square root of 2 into sigma square hat minus tau whole square divided by 2 sigma square, and integration over tau. This is basically definition of a convolution integral from these two functions. So by separating the independent constants, we have 1 by 2 pi into sigma square into 1 by 2 into integral 1 by square root of tau into sigma hat square minus tau into exponential of minus tau by sigma square, that is from the first term, and from the second term we have minus sigma hat square minus tau divided by sigma square. d tau. We can clearly see that the tau by sigma square and this minus tau by sigma square cancel each other, and we are left with 1 by 4 into pi sigma square into exponential of minus sigma square hat divided by sigma square into integral 1 by square root of tau into sigma hat square minus tau d tau. And we can clearly see that the limits of tau should be equal to 0 to sigma square hat, since y0 plus y1 is actually equal to sigma square hat. Now our goal is to derive this integral or evaluate that integral. So integral 0 to sigma square hat 1 by square root of tau into sigma square hat minus tau d tau. This integral can be easily evaluated by using parametric substitution. That is, tau is equal to sigma square hat into sine square theta. Then sigma square hat minus tau should be equal to, the derivative is equal to d tau is equal to sigma square hat into 2 sine theta cos theta d theta. And this function, that is 1 by square root of tau into sigma square hat minus tau, should be equal to 1 by square root of sigma square hat into sine square theta into sigma square hat into 1 minus sine square theta. And this is obviously equal to 1 by sigma square hat into sine square theta into cos square theta. And the root becomes sine theta into cos theta. And the limits are obviously for tau is equal to 0, theta is also equal to 0, and tau is equal to sigma square hat is theta is equal to pi by 2. And because sine theta becomes 1, theta is pi by 2. So the integral becomes 0 to pi by 2. And the numerator is d tau, which is obviously, and the numerator is d tau, so which is sigma square hat sine theta, 2 sine theta cos theta d theta. And the denominator is sigma square hat sine theta cos theta. So apparently this integral is equal to pi. Since sine theta and cos theta cancel each other, and we are left with integral d theta, integral 2 times d theta, and the limits are 0 to pi by 2, so this integral should be equal to pi. Therefore, the PDF of sigma square hat is equal to pi by 4 pi into sigma square into exponential of minus sigma square hat divided by sigma square, which is basically a gamma integral, that is a gamma PDF, that is 1 by 4 into sigma square into e power minus sigma square hat divided by sigma square, which is a gamma PDF. Thanks for watching.